Welcome to inverse functions. It's gonna get freaky. We're gonna mix things up a little bit. So find the inverse of the set A. So just a refresh, inverse means opposite, and it's also denoted as that -1 value. And basically all that it means is that you literally flip x and y. So the inverse of this set flips around. So we're literally flipping the domain with the range. So like the domain of the original function becomes the range of the inverse function. So the next question says find the inverse of f of x equals 4x, then verify that both f of 1x and that they're the same. So we're looking that if we take, they should equal the identity function. So let's look at the inverse. So the first step is that we write y equals 4x, we switch x and y, and we solve for y. So our inverse is x over 4, which that makes sense too, because the opposite of multiplying is division. So now we're verifying what happens if we do this composition of functions, if we take the inverse function and we plug it into the original function. Hey, look, we get x. What happens if we take the original function and we plug it into the inverse function? Hey, look, we get x. So we know that that is our inverse function there. And so this just kind of talks you through. You can read through that on your own. It tells you that if we have the inverse, if we do the composition of functions, we should get that identity function of just x. Okay, next, which of the functions is the inverse of this? Well, let's check. Write y equals. That's the first step always. Switch x and y. Anytime we're finding inverse, it follows the same exact steps. So now to solve for y, we're going to have to actually cross multiply. And this is just a 1 here, so we're multiplying there. And then we are going to have to solve for y, so we can divide by x. And then we add 2. And so we can see this is the inverse function. We could have done it that way, or if you wanted to, you could have looked at them and seen which one would plug in to give you the identity function. Okay, verify that the functions from the previous example are inverses of each other graphically. Okay, we can do this. We have a calculator. This is great. So we're going to plug in our previous inverses, which was the original function was 5 divided by x minus 2. I'm putting parentheses in just to keep the numerator and the denominator separate. And then our inverse was 5 over x plus 2. All right, so when we go to graph these, you can plug them in and graph them. This is just my normal zoom window here. So that's the original function, and then this is my inverse function. And how do I tell if they are inverses of each other? Well, we would have to see if they flipped x and y. Like at this point, we have the point 42, and our graph should be at the point 24. So you can see, like on each of these points, it flipped our x and y's to actually make that inverse. You could do that for any point. 0, -3, so it should be at, or 0, -2.5, so it should be at -2.5, 0, which is where your red function is. It's flipping your x's and y's. Okay, next, verify that the functions are inverses of each other numerically. And so for numerically, that means that it wants us to use our graphing calculator and to use the table function. So let's see, and we can see if the x and y's are flipped. So these are just lots of different ways of doing the same type of thing. I'm doing this so that then I can pull up my table. We can look at the graphically one too, just to compare here too. Looks like it's pretty good. So our table, okay, look, at 0, we're at -2.5. Let's see where we're at -2.5. We're at -3.75. But do you see here? Look, so at 0, we're at -2.5 on y1. But if we're at -3, if we're at -2.5, we're at 0 on y2. Do you see how these flipped? And we could do the same thing here. Like if we're at 1, we're at -2 on y1. But if we're at -2, we're at 1 on y2. It's flipping it around for your x and y's. So we know that this one numerically is an inverse. So it says to have an inverse function, the function must be 1 to 1. So remember, a function means that we don't share x's, but 1 to 1 means there's no two elements that correspond to the same element in the range of f. So for a function, you can have like multiple y's like going to, like you can't have multiple y's going to the same x, but you could have some different shared values. But for a 1 to 1, it means every x has its own y. There's no more repeats there. And so a function can only have an inverse if it's 1 to 1. So the first thing just asks us, is the function square root of x plus 1 1 to 1? Well, let's see. Let's plug in. The way to check this is we can say square root of a plus 1, does that equal the square root of b plus 1? We're just plugging in two values to see what happens. If we subtract 1, we get square root of a equals square root of b. Square both sides, we get a equals b. So there's nothing else that could imply. So we know that f of a equals f of b. This implies that a equals b. So essentially what we did was we just plugged in two arbitrary values, and then we went down to see if they would still equal each other. The other thing that you can do is you can do a graphical solution. This is probably the easiest way if you have access to a graphing calculator for the problem, because all that you're doing is you're checking the horizontal line test. Is there anywhere that this is going to be sharing any values on the vertical and the horizontal line test? Vertical line test passes and horizontal line test passes. So yes, this is 1 to 1. All right, so this one is telling us like how to find the inverse function, which is what we've been doing, but the steps are written out here for you if you need it. First thing to do is to use the horizontal line test and the vertical line test to determine if it is an inverse function, if it is 1 to 1. So let's start this for this one. 5 minus 3x divided by 2. Okay, that looks pretty great. Horizontal and vertical, no points that we're crossing at multiple points there. So happy about that. So then now what we do is we just replace f of x with y. So we write y equals, just like we've been doing. Then we swap our x and our y. So we swap our x and our y. X equals 5 minus 3y over 2. And we solve for y. 2x equals 5 minus 3y. We subtract our 5. So we get 2x minus 5 equals 3y. And we divide by 3. We get our inverse function. We can write this at the end like this. And if we wanted to double check, we can plug it into each other, right? I'm gonna leave that one for you to do. See if you can plug that in for x there and see if you come out with x. See if you can plug this in for x right there and see if you come out with x. All right, last one. Inverse function y equals x squared. Let's see if we pass the horizontal line test and the vertical line test for x greater than or equal to 0. So we have this function. This would not pass the horizontal line test, except that our domain says it has to be greater than or equal to 0. So we're not including anything where x is less than 0, so it would actually pass our horizontal line test since we're only looking on that side. So let's start our steps. Y equals, switch x and y, solve for y. And that is our inverse. And then you could go back and double check that they are, in fact, inverses of each other. This would have to continue like in the correct domain though. All right, thanks guys.